Hi, my name is Katie Wang, and I'll be covering my constant velocity lab. The purpose of this lab is to record the constant horizontal motion of an object to observe the object's position over a period of time. At the end of the lab, I could compare my predicted and observed position versus time using an Excel graph. As you can see, the predicted and observed velocities are nearly the same except towards the end, where the observed position is drifting away from the predicted position. One principle in this lab is Newton's first law, which states that objects in motion will remain in motion unless acted upon by another force. We can apply this law here because the net force acting on the object is zero. This leads to the object having a constant velocity. Another principle is Newton's second law, which states that the acceleration of an object is dependent on the net force acting upon the object and the mass of the object. Newton's second law also includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we're interested in an object's future velocity and position. Finally, an assumption we make during the experiment is that drag and friction are negligible. For my video, my system is the bottle, which is my object, and the surroundings is the desk. I position my coordinate plane in the center of my object, so my object moved along the negative x-axis at a constant speed. I use my desk length as the scale calibration. I also ended up clipping the beginning frame and tracker and the ending frames to my phone's Photos app to account for acceleration and deceleration. My initial conditions are shown here. For velocity, I picked two data points and calculated it using this formula. You can see the graph has a constant negative slope because my object is moving in the negative x direction at a constant speed. Here are the parts of the code that are important to this lab. For the mass of the bottle, I estimated it to be 90 grams. I plugged in the initial position and velocity in the x direction that I calculated earlier. Then I changed the delta t to 0.03 seconds because that's the size of each time step in tracker. For lines 58 and 60, I replaced the original vectors that are here with the variables in the velocity and position update formulas. And this loop runs while t is less than 2.33 seconds because my object was moving at a constant velocity for that time. When I put my data from Tracker and GlowScript together on an Excel graph, this is the result. You can see that the two slopes begin similarly as a downward slope, but the observed position begins to differ a bit from the predicted position towards the end. Some possible explanations for this could be human error when determining the center of the bottle inside Tracker, how I estimated the bottle's mass instead of using a mass, human error when setting the calibration stick in Tracker, or how GlowScript does not account for the force of friction. For our what if question, if I had used the positive x-axis instead, then my graph slope would be upwards positive. This means the direction of the velocity vector is the opposite direction, but the magnitude of the velocity vector is the same. The concepts from the previous slide will also remain the same. And for our what does it mean question, we observed two forces in the computational model, the gravitational force pulling on the bottle and the normal force exerted on the bottle from the desk. These two forces cancel out to result in a net force of zero and a constant velocity. However, in the real-life experiment, we may have observed more than two forces, as drag and friction could have been present. So to conclude, in this lab, we used Newton's first and second law to predict the motion of an object. We recorded and analyzed horizontal motion of a bottle moving at a constant velocity in Tracker and compared the data to the GlowScript computational model. And we noticed the possibility of friction or drag that makes our experiment differ from an ideal experiment.